All right, today we're going to learn about an incredibly relevant topic. It is the phenomenon that's responsible for almost all of the electricity you use in a given day. It's known as electromagnetic induction. Well, Michael Faraday, a famous physicist from England, discovered that when you, let me grab my red pen, that when you have a scenario such as this and you close the switch, if you look at what we have here, we have a battery connected to a coil of wire, which is a solenoid, and then back to the battery. So a very low resistance setup here without many items in the circuit. And over on the right side, we have a current meter or an ammeter. And the ammeter is connected to a solenoid and then back to the ammeter. So these two circuits, the left side and the right side, are not connected electrically at all. Now they are wrapped around the same iron core. This is just a round piece of iron. So that helps the loops to communicate with each other, but they're not electrically connected. As a matter of fact, the right-hand side doesn't even have a source of potential difference, so you would never expect current to flow. So what Mr. Faraday discovered is when you close this switch, you would get a momentary deflection in the needle. Now, the deflection wouldn't last very long. It would just be a quick blip, and then the current would shut off after you have the switch closed. And then he noticed that when you open the switch again, you would get a deflection in the other direction. A very quick deflection, it doesn't last very long, and then it would quickly go back to zero. So what he was noticing is that you are getting some current to flow in the right-hand side of this circuit when there's a change in the current over here. So here we have this current, and you might think in your brain when you were doing electricity and you turned the circuit on or you flipped the battery on or connected the power supply, that the current went from 0 to whatever value it needed to be at very quickly. Well, it does happen very quickly, but it doesn't happen instantly. So while that current is ramping up, that's when you get the effect over here on the right. So as long as the current is changing, and if the current is changing, the magnetic field is changing. That's the important part, because we have a solenoid here. So whenever the current is flowing, you're going to get a change in the magnetic field. Well, those magnetic field lines puncture through this coil, and that's what's causing the current over here. So whenever you have a change in current or magnetic field, that gets communicated over here, and that changing magnetic field ends up resulting in a change in current, which you can read on the current meter. Now, as long as you keep the switch closed, the reading will go back to 0 because there's no change occurring. So this phenomenon is very much linked with change. You're only going to get an output when you have a change in the input. So the official definition of electromagnetic induction is a changing magnetic field, which was caused by our changing current, can create or induce, that's where the name induction comes from, a potential difference in a wire. Now the potential difference, as you know, can be also, we can also use the word voltage, or in this slideshow, we're going to use EMF more than anything else, electromotive force. I'm not particularly fond of the term, but this is the old school term for potential difference or voltage, and it's usually written with a script E, a Greek epsilon, I believe. So if you have relative motion between a magnet and a coil, you will get an induced potential difference. Now, on the previous graphic, we didn't have relative motion. We just had a changing magnetic field. But if you were to move a magnet near a coil, you would also get a changing magnetic field through the coil, and that would induce a potential difference as well. So this is kind of method number 2 to get an induced potential difference. And if there's a complete circuit, you're going to get some induced current. So up above here, we've been talking about an induced voltage or an induced potential difference. And you'll get that even if you have a broken circuit. But if you have a complete circuit, you will not only get the induced potential difference, you will also get a current to flow. So in many of the problems, we'll be calculating induced potential differences and induced currents. All right, let's look at a qualitative example. In the original graphic, I described that when Mr. Faraday closed the circuit and got current to flow, he got a deflection in one direction, and when he opened the circuit, he got a deflection in the other direction. Now, why is that? Well, that comes from something known as Lenz's law. Lenz's law helps us predict the direction that the current will flow if you have induction going on. And here's the key. The current will flow in a way so that the change that's happening will be opposed. Think of it this way. Think of the loop, this opening in the loop is territory that needs to be protected from changing magnetic field lines. If you start adding field lines or removing field lines, the loop is going to be unhappy because loops are like people. They don't like change. And that change can be fought by creating a current which will make itself a magnet that will try to oppose whatever change is creating it in the first place. I know it sounds a little confusing, but let's take a look. So let's first pretend that this isn't moving. You would have no current flowing in this coil over here because whatever magnetic field lines are puncturing the loop would not be changing. Now if you begin advancing the magnet toward the coil, you're going to get, remember there's a magnetic field surrounding a permanent bar magnet. We looked at that during magnetism, and the field lines run from north to south, so they would all look like that. So let's say when it's far away, there are no field lines through the coil's opening here, and as you begin advancing it, you're going to get magnetic field lines that begin to puncture through the loop, and the loop is not going to be happy about that because loops don't like change in magnetic field lines. So how's it going to fight that? Well, it's going to create a current in itself, a potential difference in itself, to try to fight the change that's opposing it. Well, how would this poor coil fight the opposing magnet? Well, it could do so by creating a north pole here, because you have a north pole on the right side of this magnet. If you created a north over here, since the like charges repel, that might try to slow down the advancing magnet. Now, it's never going to win. The poor coil's always fighting back, but never wins. You're, of course, going to be able to push this magnet toward the coil, but you would definitely feel the opposition if you were sitting in class and I gave you the magnet and you pushed it toward the coil. You would feel the opposition to it. So how would it create a north pole here on the left side? Well, remember our hand rules for magnetism, the right hand rules, and we're talking positive current here. All of this current that gets mentioned in all of magnetism is conventional current or positive current. So in order to create a north pole on the left-hand side, remember this is where you wrap your fingers in the direction of the coils, and your thumb tells you the direction of the north pole. So if you want your thumb to point to the left side of the iron core, you would have to wrap your fingers up and over the front of the iron core. So that would get the current to flow in the direction that I'm indicating here. I'm not going to say clockwise or counterclockwise because it depends which way you're looking at the coil from. But definitely from our view here, the current would be flowing up and over the iron core, and that would create a north pole here. Now, let's say you advance the magnet all the way too close to the iron core, and then you stop. There's going to be lots of magnetic field lines through this solenoid, but the coil really doesn't care, because once you stop moving this thing, once you take the velocity to zero, the coil's going to think, if I may personify the coil again, the coil's going to think, all right, I wasn't happy while you were advancing because it was changing the magnetic field lines through my interior, but now that you're already here, just stay here because I don't like change. So the loop is ambivalent, whether there's a lot of field lines through it or no field lines through it. It just doesn't want change. So if you leave the magnet stationary, you will get no current to flow in this coil. Now, what happens when you start moving the magnet away from the solenoid? Well, now the loop thinks again, okay, you're moving away. I'm not happy about this because now the number of field lines through my interior are decreasing. So I want to fight the change that's opposing it. Fight the change that's opposing it. So the only way for this poor solenoid to fight back against the receding magnet is to try to create a south pole on the left side of itself. Now, it's not going to win because you're still going to be able to pull the magnet away, but it's going to fight the change that's creating it. So if you take your hand and do the hand rule, your thumb is going to want to point to the right side here, which means you would need to, without hurting yourself, wrap your fingers from the top side to the bottom side around the front of the iron core, and that would notice that your fingers would wrap this way. the current would flow toward the bottom, which is exactly the opposite of what happened on the top, which is why in Lenz's law, you see deflection in one direction when you do A, and when you do the opposite of A, B, you would get the current to flow in the other direction. Now, that was all very quantitative. It's time to get quantitative. Um, so what is the magic quantity that if you change it, you will get an induced potential difference? That quantity happens to be what's called magnetic flux. Magnetic flux has three pieces to it. Magnetic flux, first of all, gets the Greek letter phi. So this phi b here is magnetic flux, and it's composed of, here, let's just go ahead and reveal the rest. It's three quantities multiplied together: magnetic flux, magnetic field strength, which is of course measured in Tesla, the area of the coil, so this would be a rectangle down here in the lower right, you would find its area in square meters, and cosine of theta. Well, where is theta coming from? Well, theta is going to be between two vectors. The first vector is the magnetic field line direction, which would be like this, and the other would be this little area vector. So obviously the area of the loop doesn't have a direction, so people give it a direction by making a little perpendicular to it. So this theta is really the angle between the magnetic field lines and a perpendicular to the loop. So in this particular case, the angle would be 0 degrees between this fictitious perpendicular to the loop and the magnetic field lines. That's the best possible case. You get the most flux when the field lines are perpendicular to the loop. If you were to have field lines parallel to the loop, well, they wouldn't puncture the loop at all, and you wouldn't have any magnetic flux. And if you look at the units here, you're basically going to have magnetic field strength times area, which would be Tesla meters squared, which is given a fancy name. It's given the name a Weber, or AWB. So if you change this quantity in any way, now you could change any of the three quantities, and you would get an induced potential difference. I could make the magnetic field strength weaker or stronger. That's what I was doing when I was pulling and pushing the magnet away. I could change the area of the loop. You could take the loop and squash it, or if it's a loop, you can kind of pull on the loop and change its area. And you could also change the angle between them. You could go, if you were spinning this loop in the magnetic field, that would be changing the theta. So if you change any or all of these three quantities, you are going to get a potential difference to flow. So this is a quantity that can be calculated. So the top of the mountain here in induction is known as Faraday's law of induction. And it says the EMF, or the induced potential difference, the induced voltage, is going to be the rate of change of the magnetic flux. So this is delta phi over t, or delta BA cosine theta, because this is the term we just learned for flux, divided by t. Now, the way you'll use this equation is this delta operator can apply to either the B, the A, or the cosine of theta, and then the two things that aren't changing will pop out to the left of the delta. So you only leave the delta operator in front of the thing that's changing. So a couple of quick notes here. This E is EMF, or voltage. Here's some good wording. The magnitude of the induced EMF, or voltage, is the rate of change. Notice the T in the denominator. The rate of change of the magnetic flux. Remember, the thing that's in the numerator is the thing that's being rated. So this would be the rate of change of the magnetic flux. If you had a graph of magnetic flux versus time, that's a phi, magnetic flux versus time. If you had that graph, you could simply take the slope of this graph, and that would give you the induced EMF. And this equation here, as usually written, is for a single loop. If there was more than one loop, you could think of there being a small n out in front of the equation. So if you had 10 loops, you would put a 10 out in front, because you would get this effect for each and every one of the loops. All right, let's take a look at a numerical example. A magnet is pushed toward a single loop of wire, so N is going to be 1, increasing the magnetic field strength in the area of the loop, which has a 6 centimeter radius, from 0.05 Tesla to 0.25 Tesla in 0.10 seconds. So the thing that's changing here is the B. So first they ask, calculate the original magnetic flux. So calculating flux is a thing, not even calculating the Faraday's law of induction, not even calculating potential difference. So let's first calculate the flux, our magnetic flux, which is phi b. Sorry for the penmanship here with my mouse. That's going to be the BA cosine theta. All right. The B, well, we're looking for the original flux, so we would put the original magnetic field strength, so that will be 0.05 Tesla. In the area, we have a circular loop here, so it has a radius of 6 centimeters. So let's put a bracket, and that's going to be pi times 0.06 meters, and that's going to be squared. So pi r squared would be the area. And then in a problem, typically like the graphic I showed you before with the magnetic field lines that are parallel to that A vector, perpendicular to the plane of the loop, you would just assume that you have a 0-degree angle and that term would disappear. So it would just be 0.05 Tesla times the area of the loop, and that would get us to 0.00226. 0.00226, and either Tesla meter squared or Weber. Now, calculate the induced EMF during this. Well, the induced EMF is going to be delta phi over T. That's a delta out in front there. Now, the thing that's changing is the B. So it's going to be, well, let's just calculate it. Delta B is going to be B final minus B initial. So B final minus B initial is going to be 0.20 Tesla. And then we still need the area of the loop in there. So pi r squared. So 0.06 meters, quantity squared. That's 0.06 meters. So B, A, cosine theta, we'll leave that out because we're assuming it's perpendicular to the loop here. And the time, 0.10 seconds, goes in the denominator. So we'll end up with, if you do the math, 0.0226 volts. Actually, that number shouldn't be the same. Actually, I miscalculated that. I had it written down and I wrote the wrong number. We're going to get 5.65 times 10 to the negative 4 Webers. That's a 4 right here. 0.05 Tesla times pi times r squared. 5.65 times 10 to the negative 4 Webers. And then this is the answer to the induced EMF. All right, our final slide. There's another equation that you should know about for induction. This essentially comes from Faraday's law, and it has to do with just if you take a single conductor and slide it through a magnetic field. Now you might think, well, I'm not really going to get current to flow because this is not a complete circuit. It's just a chunk of wire. Well, you're right. You would get an induced potential difference between the ends of this conductor, but you really wouldn't get a continuous current to flow. Think of this as if this was an airplane, and this could be the tips of the wings of the wing of the plane. If you put a voltmeter between the ends of the wings of the plane, you would be able to measure whatever the induced voltage is between the ends of the wings, which would be called the motional EMF, which I like to call E-motional. So how do we calculate it? You got to be careful here. This V is now the velocity of the conductor. This is not the induced potential difference. Here's your induced potential difference, and you get it by multiplying three things together. The speed of the conductor, the magnetic field strength in Tesla, the length, so the length of this conductor in meters, um, and then the angle between the velocity and the magnetic field lines here, which you may remember the x's are into the page, so that's a 90-degree angle. So typically when you have the wire moving perpendicular to the magnetic field lines, you're going to have the sine of 90, which is 1, which is the best this can be, and that would go away. So typically this just becomes E equals VBL. And you'll have a couple of examples in the homework that use the E equals VBL. But occasionally when there is an angle, when the conductor is cutting through the magnetic field at an angle, you'll have to employ the sine of theta.